The CAP theorem, also known as Brewer's theorem, is a fundamental concept in distributed database systems that outlines the trade-offs between three key properties: consistency, availability, and partition tolerance. According to the theorem, a distributed system can only provide at most two of these three properties simultaneously. 1. Consistency. See, every read from the database returns the most recent write, meaning that all nodes in the system see the same data at the same time. Essentially, a consistent system ensures that all users see the same data, regardless of which node they access. 2. Availability. The system guarantees that every request, read or write, receives a response, either success or failure. Even if some nodes fail, the system is still operational and can serve requests. 3. Partition tolerance. The system continues to operate despite network partitions. A network partition occurs when communication between some nodes is lost, but the system remains up and running. Trade-offs in CAP theorem. Consistency plus availability. The system is consistent and available as long as there are no network partitions. However, if a partition occurs, the system might lose either availability or consistency. This setup is typical of systems with strong consistency requirements. Consistency plus partition tolerance. The system remains consistent even when network partitions occur, but availability may be sacrificed during the partition. In this setup, the system prioritizes data accuracy over availability. Availability plus partition tolerance. The system is always available and can tolerate network partitions, but it might return outdated or inconsistent data during the partition. This setup is common for systems where availability is more critical than strict consistency. Practical implications. In the real world, network partitions can happen, so most distributed systems need to choose between CP and AP. CP systems are preferred when consistency is more critical, such as in banking or financial systems. AP systems are suitable for applications like social media platforms, where it's more important for users to access the system rather than having perfectly consistent data. The CAP theorem helps database architects and developers understand these trade-offs and make decisions based on the needs of their applications. It emphasizes that it's impossible to achieve all three properties simultaneously in a distributed database system. Understanding the CAP theorem with a bank example. The CAP theorem explains the trade-offs between consistency, availability, and partition tolerance in distributed systems. It states that achieving all three is impossible, so systems must prioritize two. Let's illustrate this with a bank example. Starting a bank, strong consistency. Imagine you start a bank, personally handling every transaction. All records are accurate and up-to-date, consistency. But if you are unavailable, so is the bank, customers can't access their accounts, leading to a lack of availability. Hiring a colleague, availability. To improve availability, you hire a colleague, Pari. Now, transactions can continue when you are away. However, without synchronized records. Pari might not know about deposits you processed. This boosts availability but sacrifices consistency. Consistency protocols, consistency plus availability. To ensure both consistency and availability, you introduce protocols for immediate updates between you and Pari. Now, both of you have the same information, and customers get accurate balances, but communication delays can still cause issues. Expanding to branches, partition tolerance. The bank expands with branches in other cities, improving availability. But if network issues prevent branches from communicating, you face a choice: prioritize availability, branches operate independently, risking inconsistent balances, or consistency, wait for network recovery to ensure accurate records. Balancing availability and consistency. 1. Prioritizing availability. Each branch continues transactions despite network failures, ensuring continuous service but risking inconsistent records during partitions. 2. Prioritizing consistency. Transactions pause until communication is restored, maintaining accurate records but causing delays, leading to customer frustration. Key takeaway: In distributed systems, maintaining partition tolerance is essential because network failures are inevitable. The choice between consistency and availability depends on the system's requirements, like accuracy for a bank versus continuous streaming for a video service. Thank you for watching this video. Now you are up to speed. Like and follow for more quick tech breakdowns.